In this video, I'm gonna introduce you to Simulink toolbox of MATLAB. It is an user-friendly tool to use to solve governing equations of dynamical systems, or in other words, differential equations. So what I'm gonna do is that I walk you through an example to see how to create a model from scratch and how to simulate it. Also, I will discuss some physical interpretation of the solution to make it enjoyable for you to follow and understand the idea. Okay, let's say, just for the sake of argument, we have a vibrational mechanical system that we want to model with Simulink. Okay, so here we have a mass of M and we have a spring and dashpot or damper. Also, we have a force on the system which acts like an excitation. Here we have F naught sine omega times T. Okay, so all of us know that the governing equation of this system is as following: m times x double dot plus c times x dot plus kx equal to f naught sine omega t. Now, to solve this equation, we have multiple options to follow. One is that we know that this is a second order linear differential equation, so we can solve it by hand analytically using techniques that we have learned in differential equations. So the first approach is analytic approach. Let me change the color. So the first approach is analytic approach. We don't want to go through the procedure that we obtain the solution for this equation, but if you like, you can pause the video and give it a try by yourself. So the solution would be like x of t equal to e to the minus zeta omega n t times a cosine omega dt plus b times sine omega dt plus capital X sine omega t minus phi, which in this equation a and b are constants. That we determine them by using initial conditions. Also, zeta is equal to c over 2n times omega n, and omega n itself is equal to the square root of k over m, and omega d is equal to the square root of 1 minus zeta squared times omega n, and capital X is equal to f naught over square root of k minus m omega squared plus c times omega squared, and phi is equal to tangent inverse of c omega over k minus m omega squared. So this was the analytical solution for the equation. But another option that we have is to use numerical approaches like Euler or Runge-Kutta methods to solve the equation. So let me change the color. Category number 2, numerical. Like Euler or Runge-Kutta methods. We can write the M file and develop the solution procedure from the beginning, or simply use commands like OD45 in MATLAB, which itself uses Runge-Kutta method to solve the equation. So we can write the M file from the beginning, or just take advantages of commands like OD45. But the third option that we are interested in is to use Simulink. So number 3 is Simulink. Actually, what Simulink does is that it solves the equation numerically. So it is also by nature a numerical approach. But its advantages are that we don't need to write any code, thanks to the concept of block diagram that we have learned in control course. Another advantage is that once we learn how to use Simulink, we can implement it easily for the differential equations that are difficult or even impossible to solve analytically. But before going to Simulink environment, we need to rewrite the equation in the following format that I'm gonna tell you to make it easy to model it in Simulink. Let me just, once again, I write the equation and make it quick. Plus kx equal to f naught sine omega t. We just need to keep this higher order derivative term in one side of the equation and just move other stuff to other side. So it would be like x double dot equal to 1 over m f naught sine omega t minus c times x dot minus kx. Okay. Now, to draw the block diagram of the system, we begin with this term and just assume that we have it here at this point. So it is x double dot. We know that if we integrate this term, we obtain x dot. Okay, so here is the integrator. And if we integrate this term once again, integrated, we obtain x. So we just now need to multiply x and x dot but by their coefficient in the equation to build what is inside the parentheses. So it would be like x dot should be multiplied by minus c, and x should be multiplied by minus k, and then we add them together. So here add this term and also add this term, and also we need this term, the external force on the system. So we just add it from here, f naught sine omega t. Once we add all these terms together, we know that if we multiply the output by this coefficient 1 over m, what we will have is that x double dot. Okay, so we just build the right side of the equation and we reach where we began first. So I just connect this line to the starting point. Okay? Now we just need to build this simple model in Simulink to get the solution of the system. So let's see what the Simulink environment looks like. When you open MATLAB, there is a button over here which has a Simulink button on it. If you click on this button, the Simulink environment will open. There we are. So as you can see, there are lots of toolboxes and libraries here. But what is important for us is this box, Simulink. And also, as you can see, there are different libraries inside this toolbox. But for now, we just want to focus on two of them. One is this toolbox, commonly used blocks, which as its name implies, it has operators that we use frequently when we want to build block diagrams. The other library is this library, sources. These two libraries contain whatever we want to build our model. So let's start building our model. I just open a new model sheet here. Let me minimize these two windows so I can work with both of them. So now I just simply drag and drop every operator that I need to this blank sheet. For example, according to our block diagram, we need an integrator. So I just drag and drop the integrator operator here. Also, we need a gain operator. I drag and drop it too. Also, we need a sum operator. So here it is. We are gonna need a scope operator, which I describe its application later. So for now, I just add it to here. And for our external source, we need a sine function. So I just go to source library here. And if I scroll down, you can see the sine function, sine wave. So I add it to our model here. Now we have every operator that we need to build our model. But as you saw in the block diagram model that we developed over here, we are gonna need 2 integrators and 3 gains. So in our model, I just simply copy and paste these operators so I can have whatever number of them that I need. And now I need to connect these operators to each other according to our block diagram. To connect 2 operators to each other, for example, these 2 integrators, you just need to select one of them and press the Ctrl key down. Then select the other one. Here it is, they are connected to each other. So let me complete the connection here. I just need to connect the wire of this gain to this wire. So now they are connected, and also I need to connect this integrator to this gain. And now I add them together with the sum operator. So here I connect these 2 operators to each other, and here I connect this to this sum operator. As you can see, I need to add the sine function to the sum operator, but there is no more entry point for the sum operator. So I just simply double click on this operator and add another plus sign here. As you can see, we have 2 plus sign here, and so we have 2 entry points. And now that we have 3 plus sign, we will have a 3 entry point for this operator. So now I can add the sine function to the sum operator. Here it is, they are connected. And now I should multiply the output of the sum operator by this gain. So I connect them together too. And I know that the output of this gain is the x double dot, which is our starting point. So I just connect them to each other. Here it is. Now our model is complete. Now it is time to enter the values of this gain. So let's go back to our model over here and assume, just for the sake of argument, that our mass is 2 kilogram and our spring stiffness is 50 Newton over meter, and our damping coefficient is 1 Newton times second over meter, and also the force amplitude F0 is 5 Newton, and the natural frequency of the force is, for example, 2 radian per second. It is good also to note that our undamped natural frequency here would be omega n is equal to square root of k over m, which would be 50 over 2, which equals to 5 radian per second. So let's go to the Simulink model and enter these values. So here is our model, and remember that the first gain here, it was minus c. So to enter the value for this gain, I just double click on it, and here I can enter the value. So remember that the coefficient of damping was 1, so minus c would be minus 1. That's it. For the second gain, remember that it was minus k, so I just enter minus 50, and here it is. And for the third gain, it was 1 over m, so I just enter here 1 over 2, which 2 is the mass of the system. That's it. Also, we need to enter the parameters of the sine function and the initial conditions for this integrator. So for the sine function, I just double click on it, and as you can see, there is a formula for the sine function, which in this formula we just need to enter the amplitude for the sine function and the frequency. We know that the phase and the bias in this example are 0. So the amplitude, remember that it was 5 and the frequency was 2. So that's it. This is for our force. And for these two integrator, remember that the first integrator, when we integrated the x double dot, we obtained x dot. So here, as I double click on it, the initial condition would be for the x dot, initial velocity. So here we just assume that the initial conditions, both of them are 0. So initial condition for this integrator is 0, and for this integrator, which the initial condition for it means the initial displacement, also we consider it to be 0. We are almost done. I just need to explain the application of this scope. We use this scope to monitor the behavior of a parameter that we are interested in. For example, in the equation that we had before, the differential equation, here we are interested in the displacement of the mass x of t. So in our Simulink model, I just connect the wire of this scope to output of the second integrator, which we know is x. And that's it. Now our model is complete and it's ready to be solved. To solve the model, you just need to hit this button, run button. So once you hit it, and there it is. Solution is done. So if you double click on the scope, this is the response of the system, x of t. But as you can see, this is not a smooth curve. We can do better than this, right? So in order to get a better curve for the response of the system, I just need to change a few parameters. Here in the main Simulink window, under the simulation tab, there is an option which is model configuration parameter. Also we have it here. It's like a gear button. So if you go to this option, there is a window, here it is, which As you can see, there are lots of parameters that you can change their value, but for now I just want to explain two of them for you. The first one is the maximum step size. Actually, this is the maximum step size for the time that software uses when solves the equation numerically. And as you can see, its value is chosen automatically by default. And we need to change it to a relatively small value in order to get a smooth curve. So I just change it to, for example, 0.01. That's it. The other parameter that I'd like to explain for you is that the time interval that the software solves the equation. By default, it solves the equation for 10 seconds, but we can change this interval. For example, I can change this value 10 seconds and put a 40 seconds here, and now the software solves the equation for 40 seconds. So that's it. Now we are ready to run the simulation. To do this, we just need to click on this button, Run. And here it is. The solution is done almost in a second. So if we look at the scope, here is the solution. And here you can see that we have a much better curve relative to previous one. It is very smooth. And also we got the solution for 40 seconds, not just for 10 seconds. To review the procedure, remember that we began with the differential equation of motion here. And what we did was that we just wrote the equation in the standard format for the Simulink. And according to this equation, we drew the block diagram of the system. Then we built the exact copy of this block diagram in the Simulink environment here. And we just ran the simulation and got the response of the system. As you can see, it is a very fast and simple approach to get a response of a dynamical system. Also note that in most of problems that we have in control course, we already have the block diagram and we just need to build it in the Simulink to get the response of the system. But here I also showed you how to start from the beginning when you have a dynamical system, which you can write the governing equation of it. And then you can build the block diagram based on that equation, following the technique that I showed you. For now, to get a better sense of the response, let's change the value of some physical parameters of the system and see how the system response would change. Just remember here, when the damping coefficient is 1, the maximum amplitude of the response in the steady state part is equal to approximately 0.12. Okay, so now let's increase the value of the damping. For example, if I change it to 15, if we increase the value of the damping, we expect that the amplitude of the response to decrease. So let's see what will happen. I run the simulation, and if we look at the scope, here it is. Now the maximum amplitude of the response is approximately 0.10 or even less than that. So we increased the value of the damping, and as we expected, the maximum response of the system decreased. Let's follow another scenario. For example, if I put damping equal to 0 here, I change it to 0, we expect to have a larger maximum amplitude for the system, because now we have an undamped system. So if I run the simulation and look at the scope, you can see the maximum response is larger than 0.15, which is even larger than 0.12 that we had before. So we can also try another scenario. For example, here if I change the frequency of the excitation, remember that in our model the natural frequency of the undamped system was 5 radian per second. So if I increase the frequency of the excitation, so that it would be close to natural frequency of the system. For example, I change it to 4, we expect that the maximum response of the system to increase. So here I run the simulation. That's it. You can see that now the maximum response of the system is close to 0.5, which is really larger than previous values that we had. For example, for another scenario, I can put the excitation frequency exactly equal to the natural frequency and see what will happen to the response of the system. So I run the simulation, and here, as you can see, as the time passes, the maximum response of the system will increase, which we call this phenomenon resonance. So like these examples that I explained to you, you can try other scenarios. For example, one can assign a value to the damping of the system, damping coefficient, and put the excitation frequency to be equal to the natural frequency of the undamped system, and then see what will happen to the response of the system. Actually, there is so much more that I love to share with you about the operators here in Simulink environment and also other libraries. But hopefully this basic review of Simulink covered enough to get you started and explore on your own. Thanks for watching.